Hi, I'm Lydia. I'm a mechanical engineering student here at UAF.
I'm Jack. I'm a mechanical engineering student at the University of Minnesota Duluth.
Yeah, so this summer, our internships were overall an overview of marine energy, from research to data collection to data analysis. And I worked with Eloise Brown for ACEP data collection. We both worked with Steph Fisher at the Tanner River test site.
And then I worked with Emily Browning Alvarado on some 3D printing stuff. There's our presentation overview. You've seen these before.
Yeah, the only difference is we'll talk about our stuff together and then separately. Yeah, so bottom line, my part of this internship was doing marine resource assessment in Kotzebue, and Jack was doing 3D modeling of the riverbed in Tanana River, and then we were both at the test site half of our time, helping out Steph and being part of Sharks testing by Blade Runner, which is a hydrokinetic turbine testing. And one thing to make clear is the difference between hydrokinetic energy and hydroelectric energy. Hydroelectric energy is dams, but hydrokinetic is run-of-the-river energy. So just like wind power is airflow with a turbine, this is river flow or tide flow with a turbine in the water.
So research project goals. I wanted to create a tutorial for turning the bathymetry and drone data into a 3D printable model. And then also learn about the testing process for new hydrokinetic technologies. And then Lydia was working on developing a workflow for MHKit to analyze the Kotzebue data.
Yeah, so I guess what's the purpose? Why do we care about this? What is marine energy? For ACEP's scope, marine energy is doing resource analysis, so collecting data about the potential for marine energy in places in Alaska. And then in Nenana, we're testing different technologies like Blade Runner. And then why do we care about this? There's so many small communities in Alaska that see river water ripping through the communities, and they're like, wow, that's a lot of energy. How can we harness that? And same for coastal communities. I grew up in a coastal community, and there's 20-foot tides where you're like, wow, the moon's doing a lot of work here. How can we take some of that? So, and it still is it's very much a developing technology. Like wind and solar, they're standardized, and you have them, you see them places, but hydrokinetics is still in the design stage, and that's why the Tanner River test site is so cool. So my part of the internship was kind of backwards. I started out by doing data analysis from last year's Kotzebue data, and I was utilizing MHKit, which is the Marine Hydrokinetic Toolbox by the Department of Energy. It's mostly funded through them, but the national labs are working on it. And I started out using the MATLAB toolkit, but it wasn't as developed as Python. It was using Python wrapping, which killed my computer. I went through 2 computers, and it wanted like 7 terabytes of RAM, and I just was never going to get that. So I switched to Python, and Andrew Sims at the National Renewable Energy Laboratory was a great resource, and Vax was really helpful with a lot of my Python code. So I eventually got some good grasp from that. But then outside of the office, I was programming instruments, deploying them, and collecting data in Kotzebue with Elle. So in July, we traveled up there, and we talked to the utility about the possibility of marine energy and why they want a resource assessment there. And then we programmed and deployed ADCPs, acoustic Doppler current profilers. So that's what that black device on the left is. It's got 5 beams, so it's 5 sonar beams collecting velocity measurements using the Doppler effect. And then along with that was a CTD, a conductivity, temperature, and depth sensor. And that was mostly in the water for collecting salinity measurements. And then the little yellow buoy there is an acoustic release. And that's so that at the end of your data collection, this buoy pops up and you know where your mooring is at the bottom of the ocean. And the mooring is this orange guy right here. It says sea spider. So it's sitting in the bottom of the Kotzebue Channel right now with 150 pounds of lead weights on it. So it should stay there. Yeah. So some background information about Kotzebue. They're super interested in getting really renewable really soon. And so part of that, they're like, what about our river channel kind of going through here? And it's not really river channel. It's part tide, part river. If you see on the right-hand map, there's 3 massive rivers, the Noatak, the Kobuk, and the Selawik, that are all being funneled into this area right outside of the city of Kotzebue. So if you're standing on the shore in Kotzebue, you see the water moving as if there's a river right there, but it's not. It's Chukchi Sea. And so there's this combo of tides and then a pretty strong river channel coming in. The graph on the left is from Andy Mahoney and in Kotzebue, and so it's really helpful. The star is where last year's mooring was. That's the data I'm currently working with, and it's there because the city permits didn't quite work out. And so this year it's in the green dot, which is a much stronger velocity area. So when Elle and I were there, it was a very interesting conversation to keep having with the utility and the native village and the borough. Such an important part of research is talking to the people where you're doing your research and being like, do you want this? And the utility asked us to be there, so we knew they wanted it. But there's a lot of controversial parts of this project because the city is super concerned about subsistence in that area. That's a heavily trafficked seal and beluga whale area, and subsistence is such a huge part of their lifestyle. They're really concerned about it. So this is very much like a, maybe you have enough velocity for a turbine, maybe not, and we'll have the data for you if you want it. So these are my preliminary results from MHKit, and on the right is a graph of velocity, and it's in depth bins, so it's the entire water column, and the top line, the jagged line, is the surface of the water, and the dotted line is the mean surface of the water. So the dark red and dark blue is the strongest velocities, and we're really looking for 1 meter per second or bigger for a turbine. And the reason that this isn't too strong is that its principal bearing is east. So red is east and blue is west, but if you look at the map, it's more like northeast, southwest. So whenever, it's Elle's job now, but we'll rotate that to be more correct. And you can really see that in my favorite graph is the compass on the top left. You can tell that the strongest current is going in the southwest direction, because even though there's a little northeast for tides, the southwest is all those rivers just forcing the current that way. So along with actually doing data analysis, I was trying to streamline a workflow for PMEC, the Pacific Marine Energy Center here at ACEP, for their ACP data process. So there's 3 scripts that I worked with. The first one, the quality control script, is pretty much verbatim the National Renewable Energy Laboratory example for ADCPs. So it's just like put a file in and see how it looks. And then in order for my computer to accept things, I made 2 more scripts. I saved and averaged all the specific files in NetCDF, so they're smaller, and they've been processed through the ADCP toolkit. And then the final file is, the final script was putting all those little NC files together and then plotting them with all these cool plots. The last slide had the velocity, direction, and rows plots. And then I also have depth, flow speeds, just magnitude of velocity, and turbulence. And the MHKit link is right there, but then also all of my scripts and this workflow are going to be on GitHub once the pull request goes through. All right, lastly, my lessons I learned this summer, some challenges I had was the Python versus MATLAB thing where I kept having memory issues and just sitting there and running it for a few hours, and then it just stops and goes, you don't have enough memory, and I'm like, you're telling me. And then when Elle and I were in the field, I definitely saw the reality of fieldwork in rural Alaska. Growing up in rural Alaska, this shouldn't have been a surprise to me, but we had to stay there a couple extra days because our batteries didn't get there in time. But we had fun. It was 4th of July. But yeah, so my biggest takeaways is that research is really just active problem solving. You're making a plan, things go wrong, that's okay. It's good to have a plan, but things are gonna go wrong, so you just gotta kind of wing it and work through it. And that's actually really fun and it's really satisfying when it actually goes well in the end. Also, I found this in the office in the field. When one tool isn't working, there's another one that other people have used for a while and they like and works well, like MATLAB versus Python for this specific data set, or just you're on the barge and you're trying to build something and you're just like, I need a different wrench. But yeah, overall, I think the biggest thing I learned about myself was that being in the field is really fun, and I can't have a job where I'm only at the desk. I love that hybrid of doing your desk work, getting the data analysis done, but also getting outside, being on the river, and getting your hands dirty doing hands-on work.
Well, and then my research methods, Google was very helpful. So my whole thing was trying to figure out how to take this .xyz data, which is just a bunch of coordinates in X, Y, and Z, and turning that into a 3D printable model. And that whole process wasn't exactly documented very well online by other people. I don't think a lot of other people had done that. And so trying to figure out how do I do this, I started with some MATLAB stuff and some Python and kept running into issues. And then I eventually figured out how to use MeshLab. So I used that a lot in the process, and you'll see that a bit later. But a lot of stuff we did was just like the data collection with the ADCP, the Hydroball as well, which is basically a slimmed down version of the ADCP that you just plop in the river on a little catamaran, and it gives you depth measurements with GPS. And then also we tried to collect some data with the EBX drone there. As you can see on the photo on the right, it's a little wet. It hit some trees and then landed in the river. So we had to do a boat rescue, and I ended up using some old data from the drone from a couple years ago. But yeah, so that was the research methods. And then the whole process from the .xyz file to a 3D printable model. On the left here, you can see the Python portion. So we basically, and Emily Alvarado did the Python part, and so all I had to do was kind of generate files through this script. And so we have the bathymetry data and we have the drone data. So the bathymetry data came from the ADCPs, and that's scans of all the riverbeds, so everything underwater. And then we use the drone to take photos and create a 3D map of the banks and all that stuff. And then this script pieces those together. So you can see there's the strip of bathymetry or underwater stuff, and then the banks and the other stuff in the drone. And this script throws them together into a .xyz file. And then from there, you can take it into MeshLab, where I reduced the amount of points there were. We started with like 1,300,000 points, so it's too many. And in MeshLab, it's super cool. You can reduce the amount of vertices, and then you can also create a mesh from these points, which is basically, it draws triangles between all the different points and creates a 3D surface, kind of like a crumpled piece of paper. And then from there, you export it as an STL file into SolidWorks, where you actually create a 3D model and add that base. And then you edit it in Bamboo Studio to give it some nice coloring and stuff. So you can see what it looks like in Bamboo Studio. And then this is the final model. And then at the end, you can print it. That didn't always go right, as you can see. The printer is not supposed to look like that. But we got that fixed. It's all good now. So yeah. So there's a close-up of the final model. It's being passed around. And then I also created a tutorial on how to do this. And that's posted on the PMET GitHub. So it goes through all the steps going from XYZ to a 3D printable model. You can scan that QR code there if you want and take a look at that with your phone. But yeah, so that was the main part of my project. So yeah, my lessons learned. Creating a successful product requires many different people of all different backgrounds. So it's not just a couple engineers who build a thing and plop it in a river somewhere. It really requires so much more than that. Community outreach, all that kind of stuff, making sure that you're not having a bad impact on the environment. And another thing I learned, do your research before trying something. So I was messing around with Python and MATLAB, trying to get this whole process when I had already downloaded MeshLab, and I could have just done a little more research into MeshLab and figured out that I didn't have to make all these scripts that do nothing. And then also many things take time to do, and that's okay. You know, you get into the pacing of college classes, and it's submit an assignment and do the next one, and it's just really quick. But here it pays off a lot more to take your time. You don't have like due dates really, and then it's important and it's okay to ask questions when you don't understand something. I've never really worked with Python before this summer, and so seeing the scripts that Emily was making, they were like super high levels, some crazy stuff, and I definitely did not really understand it at first, but just make sure to ask questions, and yeah, it's okay to ask questions. And then also keep your files well organized and use checklists. Folders are nice. They're helpful when you have a ton of different models that all just look a tiny bit different. It can get a little confusing. So it's very helpful to stay organized and stuff like that.
So just to reiterate, some successes we had was that we really did see like beginning to end what resource assessments in marine energy and just research and testing really means. And we really did see how it's an interdisciplinary problem. Marine energy is, you can't just have engineers doing it. It takes everybody, the oceanographers, the test site, everything. Least favorite parts?
Yeah, waiting for prints to finish. That takes about 12 hours to do. So you can only do about one a day, and then when you have issues like I saw earlier, and you're running out of time to make models, it can be a little annoying.
Yeah, watching memory errors propagate was not too fun either. It's okay, I got there eventually. Yeah, but our favorite parts were, I think we can both say that doing hands-on work in the field was definitely a highlight, and just helping others use our process and our struggles to get a workflow going for different processes that we worked on. Then we did some fun stuff on the side. At the test site, you have to have fisheries there. So they invited us out to do fieldwork. So Deanna Strom as a researcher at CFOS, and so we were helping her collect and tag grayling in the Chattanooga River. So we were like electroshocking the river. And I named my fish Lucy. Did you?
Mine was named Norman.
Lucy was a boy, Norman was a girl. So that was, we found that out later. Yeah, this is Elle and I went to Kotzebue. So when we were stuck there, we ran the 5K and we both got medals. We got like first or second or something. That's us in the airport with our equipment, and then I got on a boat, so that was fun. And then we're assembling stuff in the big garage. KEA, Kotzebue Electric Association, let us use their garage, so that was awesome to be able to set up our stuff there. And we learned how to weld. The left is my like MIG welding conglomeration, and then
That's me, just welding.
and that's Leo helping us do it.
Did either of you, were either of you seasick, or did you know that you were prone to seasickness before you started?
Yeah, so we weren't staying seasick on the river like ever. When I was in Kotzebue, there was like, with the way the tides work and the wind and everything in that area, when we stopped moving, I grew up in Southeast. I got really seasick there, so it was bad if the Southeast girl got seasick off in Kotzebue there. But yeah, didn't have my driving.
My model that's being passed around, that's super cool.
I was wondering, is the blue part, is that the water surface or is that like the?
Yeah,
Riverbed.
so you'll see there's some higher elevation stuff. And the stuff that's lower is all from the ADCP and underwater stuff. And then the stuff that's a bit higher, so that was actually taken with the drone. So it's the surface of the water that we patched together with the ADCP stuff. Eventually, we wanted to take this hydroball data that we collected, that little strip of surface water, and piece in that hydroball data to get some actual accurate measurements of the bottom of the water there. It's too shallow to use the ADCP to collect data there, so we had to use the hydroball, but we eventually just ran out of time to add in that hydroball data. But yeah, you can make it look like water in the Bamboo Studio.